Hello. So our next speaker is Emanuil. He's a community engineer at Elastic. Hey, hello, Emanuil.
Hello, Thomas.
So he lives in London. He's always curious about how the world works in detail and interested in mentorship and inclusion. Today, Emanuil will talk us about how code tracing works under the hood in Node.js by using the Elastic APM agent. I'm very, very looking forward to this talk because I like as well discovering how things work behind the scenes. I know APM is crazy. It's very, very difficult to do. So welcome. How are you?
Well, I'm very, very good. Just rainy UK, but very nice.
Same here in Italy today, by the way.
Well, there you go.
That.
And we'll see. Maybe at the end of the talk, you'll walk away thinking that APM is not as hard as everybody thinks.
Okay, we'll see. So thank you and see you in a bit.
See you. Thank you for organizing. Hello and welcome to the gentle touch of APM. We're going to be looking at code tracing in Node.js. My name is Emanuil and I work at Elastic, same company as one of the earlier speakers today, Thomas Watson. He is in fact one of the authors of the project whose code I'll be walking you through. So let's get started. We have a lot to see. Why application performance monitoring? Why would you do code traces at all? So the way I started my career, and I think maybe on a macro scale, also it reflects how the sector went. We started with maybe you had one machine, and on it you would have an application server, web server, and a data store. And perhaps then you would separate them, and those logs would then go on 3 different machines. Then when high availability came in, you would have 2 web servers, 3 data store nodes, and 3 application server instances. And then it got more complicated. And downloading the logs from all of them for local grepping just becomes too inconvenient at some point. Also, opening top and htop on each individual one is a bit of a pain. Not to mention in the age of containers, you pretty much can't. It's very inconvenient to be opening htop alongside your main running process. So what started happening is we started collecting logs and metrics in a central location, federating them. In fact, the Elastic Stack is pretty famous for its handling of logs and thereafter metrics. And APM was something we added a few years ago. Okay, so the problem with all that is that even if you have all your logs in one place, you don't see timing information, for example. Like, yes, there's a lot of the same kind of error. Is that causing a slowdown? Who knows? Is it related to a different kind of error? Who knows? So that's where tracing is I'd say the next evolution of those 2. So I specifically had a moment that I recall very explicitly where I had an application that I was on call for, and for a few hours a day, it would get unbearably slow. And that continued for 4 days. And we only had logs and metrics at the time installed as monitoring. And so we looked at code traces, finally. And my life became a lot easier since that point. We managed to resolve the problem. It was a problem of web worker exhaustion, which was quite common. So one transaction was very slow. Once you had enough of those going, there was just nothing that could answer the phone for the homepage. And this is exactly the kind of thing that is very difficult to diagnose with just logs. Okay, so today we'll talk a bit about Elastic APM stack architecture, a little bit about the concepts in application performance monitoring, show you the UI of such a system in case, like me, you hadn't used one, even though they existed. And then the main part is, of course, a code walkthrough to see how we collect request information, errors, and things like stack traces. And then we'll chat a little bit about where you can learn more. So, tech architecture. Imagine a pretty standard app here. We have MySQL data store. We have then the backend, which we'll be digging into. That has a Node.js agent as part of it. So it's actually a dependency, as you'll see in a bit. In the front end, we have what we call a real user monitoring agent. So that's a snippet of JavaScript that gets downloaded together with your React and or Angular or Vue or whatever else client-side code you have, and essentially monitors the performance of your site from the user's perspective, network lag included. So that's a pretty nifty piece of software. Then those two agents send information to the APM server, which massages it further a little bit and then sends it on to Elasticsearch. There's just as JSON, and then it sits there as some JSON docs until we visualize it with Kibana. You can, but obviously the agents you need to download and use because they become part of your app pretty much. But the server-side pieces of software you can also download and use yourself for free, no trial period, or like that kind of limitation. Or you can have us host it for you on Elastic Cloud. If you want to avoid a who watches the watchers type of scenario where you have to have monitoring for your monitoring, then you can also pay us a little bit to do that for you. But you can get the software yourself. So, APM. Agents are little pieces, little libraries that we write that live in your app. They are language and framework specific, or they're definitely language specific, and they will have adapters for different frameworks. They will collect performance data, like how long things are taking, and set that off regularly. And on the right, show you with my pointer. On the right, it shows you the 7 languages that we support at the moment. Focus today is, of course, on Node.js. Agents collect all kinds of things, including third-party requests to third-party services, like HTTP requests if you're contacting custom tracking in Google Analytics from the backend, for example. That's the thing. SQL queries, NoSQL data stores, like Elasticsearch. I hear that's a reasonably good one. Then, of course, your code and what functions are being called. And every block, like significant major operation in your code, or a call to another service is called a span. We'll see those visually in a second. And a group of those is one transaction. Also, generally, a transaction is you get a web request in, you do some work, and then you respond. The entire process from start to end is one transaction. So generally, agents hook into libraries. If the libraries provide hooks, then that's what they will use. Often, though, there's a need to monkey patch, because the big frameworks will provide you with hooks to tell you when a request starts and ends, but they will. But other libraries will likely not have things like that. So, for example, if you have another, like say you have an HTTP client, you could patch its connect method so that you basically add a line before and a line after saying, okay, this is when it starts, and then this is when it ends. And in the middle, you call the original function, so it can do its job. Ideally, there should be very little impact in production, and there is, but there are also ways to mitigate that further. So let's have a look at the user interface and actually see some of that for ourselves. If you set up Kibana, this is very likely what you'll start out seeing. And the 3 horizontal bars left are APM. If you open that, you will see a list of services that have been instrumented. Instrumenting multiple services does make a lot of sense, and it actually brings you more than just data about each individual service, as we'll see in a second. Another cool thing here is the service map, which is a relatively new feature to Elastic APM. And this is using the span data that I was talking about, connection to data stores and other services. It maps out everything you're connecting to. So in this case, we can see that Redis, if we hover over it, is only being called by the Python service. Postgres is being called by every backend service. Yeah. And the front end, the React front end, is only talking to the Python service, which is then passing that on to other services. So this is a pretty nifty feature, just out of the box. So here we have an overview of what an APM UI would typically look like. There is a breakdown of how long we spend talking to data stores, how long we spend on application code. Depending on the different integrations, there might be a breakdown of how long we spend on the library code. This site is generally pretty fast, so app part is only 27%. Then very common transaction duration and throughput, of course, as a percentage error rate, top right. Transaction duration, interesting to note, I get 95th to 99th percentile. If you haven't seen those measures before, basically if you just look at the average, especially if it's an API, it can be very misleading because you'll have a lot of very fast transactions. But the 95th and 99th percentile are supposed to tell you more about the performance, what the performance of this thing feels like to 95 and 99% of your users or callers in the case of an API. And then we have a list of transactions, and this is one of the most useful things about an APM system. A lot goes into getting to this point on our side, but for you, the point is that you just look at it and can quickly tell what might be impacting speed and performance. The impact measure is a mixture of throughput, how many transactions of that kind, and how long things are taking. So we'll look in detail into that stuff in a second. And you have transaction types. So you have a standard web request, and you also have worker. So in this case, a standard web request is where transactions are recorded by default. They come into a web app, the web app answers them, we record timing information. But the worker is background jobs or batch processing, things like thumbnails, videos, in this case, order processing. So as you can see, these are obviously in human language. So these are things that you define yourself. They're what's called a custom instrumentation, and we'll see in a little bit how to do that. It's relatively simple, but you can do that as well. Okay, then something else that's useful to note here is that you can also see errors. So imagine that every stack trace has 20 lines, and we have nearly, okay, let's say 9,000 of this kind of error. So this in logs, this would be 18,000 lines. So it would be pretty difficult. No, actually, that would be 2 lines per stack trace. So this would be 180,000 lines, which would be pretty difficult to navigate and to diagnose anything from. So a grouping like this is just within one day, is fantastic, right? You can just go into it, see stack trace, including context. You can see exactly where your app had a problem. And if you need to, you can see the library frames. And you can see how often the error occurs at different times during the period that you've selected. In metrics, you have CPU use, including the process, and the overall system, and the memory use as well. So if you are starting a new project now, I would probably recommend installing Elastic APM first, installing an APM system first, because even if you don't end up having the time to do a proper logs and metrics setup, whatever that means to you, you already get a bit of that with functionality like this. And this is provided by many vendors, so whatever you go with, say just go with APM first. Okay, so let's have a look at the specific transaction. So we see a spike here, and it seems on average with this many transactions displayed, it seems okay, but it seems like a serious spike nonetheless. So, and indeed, if we zoom in, we see that first off, there is difficulties in collecting data during this period of time. So during some 30-second intervals, there's no data coming in. And also, there's some transactions are taking a very long amount of time. Like if there's 30 seconds, then that's presumably a timeout of some kind. So there's a problem. So we look at what's having an impact on all this. It says get transactions are having most impact. It could still be because there's the most of them. If we zoom in even further, to see individual peaks within. Okay, so things have changed a little. We still see get transactions at the top, so we'll look there first, because if they're slow and there's that much throughput, then we have a problem. But also we should note now this post has risen to the top. And in my experience, such as with that client that had a slow app for 4 days, it's sometimes some more heavy data processing that actually causes you to exhaust your web workers, and they just run out. And so you have one transaction taking 20 seconds. A web worker usually answers transactions for 50 milliseconds each. And so now it's missing out on answering hundreds of those. You know, give your app a few slow transactions, and you could very quickly be looking at bottleneck. So, all right. Well, let's say we want to look at the get one, because that's the one it says has the most impact. Okay, you'll see a very similar screen to the overview. It will be a throughput, a duration, and a breakdown. Something that's incredibly useful is a breakdown by date. So here we can see fast transactions, so taking less than 1 second. Here we can see much slower ones. So in this case, there are different services that the request is being traced through. In this case, this Ruby service down here, I can see it right up there. This Ruby service is answering quickly, but the Java service that's calling it, for some reason, is taking a very long time either to call it or for the call to return. So this is most likely a network problem, which we have to diagnose outside of APM. But sometimes you'll get errors here, and that's still incredibly useful to look at. So looking at normal transactions, what does that look like? First off, you will notice different colors. So that's what we call distributed tracing. Remember I said if you instrument all of your services, you get a lot more than just the sum of the parts. That's what you get. So the first service, as the request comes in, it's stamped with an ID. And then the next service picks up, like looks at whether there is a stamp. And if there is, it goes, oh, okay, I'll attach my information, same ID. So when it sends, when its agent sends a piece of information, reuses the ID. And then that's passed again via HTTP header to the final service. And when that agent finishes its job, it also sends its information with the same ID. And then in the user interface, those are put together. So you see the two arrows over here. That's a transaction. And then blue, we have Node. So we'll be looking at that in a second. And then those are blocks. So this is a simple app that's mostly services just calling each other. But here is one that does something else. As part of its operation, it actually issues a query. So that's calling a function or issuing a query or calling a third-party service, one span. So if we look at that span, in this case it's a Python service, if we look at that span, we see the exact query being issued, and we see line numbers, and we see context even for the code around it, and this is distinguished from the library frames around us. So, and we're also told that this is a connection to Postgres. So this is pretty darn useful to be able to see in one place. Now, looking at the node transaction, what do we actually get? So you can label transactions with your own custom labels, which we won't be looking at today. The trace ID is that stamp I was talking about that allows a request to be traced through different services. The transaction is this specific transaction ID. And this is what we'll be looking at in the code walkthrough. How do we produce this stuff? So how do we produce info about the request? How do we gather that? How do we gather all the info about the response? And also how do we gather stack traces? This is a JavaScript stack trace. So how do we gather our app? How do we gather the code around it? And what's a library frame and what isn't? So that's it. Let's get on with the code walkthrough. Right, so this is an example of an application. Actually, before we dig into this, I want to show you something else, not a standard web app. This is an asynchronous processing function. So this is a module, sorry. This is an asynchronous processing module within which we do some background job, could be video processing, in this case, payment processing. So what do we need to do to use the agent here? We need to load up APM, and then we explicitly need to call start transaction and explicitly call end transaction when we're finished. And we also give the transaction and the spans in it a label. This subtasks thing is just for the example. It's basically a function that sleeps for a while, that makes subtasks take longer so that they don't all return immediately, and we have nothing to look at in the pretty UI. So the detail of that looks like this. And so if you recall, we go from an overview of all transactions. We can click here. By default, we have just web requests. We could click on worker. And if we do, we get a list of worker transactions. And here you can see the labels that we're installing, that we're setting up in the code. And then finally, what appears as a transaction, this is the entire function being executed, and then subtasks appear as spans. And you can set that up yourselves with this start transaction. That's the name of the transaction, and that's the type. So instead of a normal request, we call it worker. I could say something like background, for example. Okay, so the reason I showed you that is so that you can see explicitly start transaction, end transaction. You don't have to do that in the standard instrumentation. So that we use web framework hooks and Node.js hooks to, basically the framework, like Express, will tell us when the request starts and ends. Okay, so this is all you need to do if you wanted to use APM in a web app node. So you load up the library, so you need to put it in your package JSON as a dependency. Then you call start, and really the only thing you really need is the service name, and because that's what appears in the user interface, some way of identifying it. I would recommend the version, and especially having the package version as a fallback, in case you haven't configured this. Because it's just a good idea to record, so you know the transaction data. If you keep historical records, you know which version of the service it relates to. Then there's tons of extra options you can pass, logging, transaction fine-tuning, sampling, and all sorts of stuff. But let's have a look at what happens when you require this. How does it actually work? And the most interesting bits. Okay, so first off, we go into we require the agent, and that's the index.js of the agent. Okay, so that requires, this is the repository right here. So that requires libagent.js. Okay, right, so I have it open here. There's an uncaught exception listener, which is interesting for us. But otherwise, it's just mostly setting options. Now, I'm going to jump forward to different places of the code which are interesting. In our application, that's the require we do, and then we're going to look at how we get the error information that you saw earlier, how we get information about transactions and what third-party stuff we rely on, and how do we get those interesting stack traces and line numbers and so on. All right, so let's start with errors. How do we record errors? There's an error handler. So basically, this will get triggered because the frameworks that are below the agent, frameworks that you're using, Node, as well as the framework like Express, the actual web framework, will tell us when there is an exception. So most of this isn't that interesting. Could just make sure that we don't add on more and more listeners so that the code doesn't get triggered again and again. So we are the only listener of this type. We do a bit of logging, and then the interesting part is we call capture error. And the definition of that is over here, capture error. We do a bunch of argument handling here, which is not so interesting, but the meat and potatoes of the issues is here, where we where we use Node.js's error capture stack trace function. So this is provided by Node.js. It creates a .stack property on the target object. When we access that later during serialization, that returns a string representing the location of the code at which this was called. So this is how we get stack trace. Now you'll see we'll see later where the line numbers actually get put in. But this is how we do unhandled exception and those groupings of errors that you saw. That's the important bit. All right, so then how do we do traces? So you saw there was a start and end to a transaction explicitly when we do custom instrumentation. The same thing happens when we do automatic instrumentation, when we simply require the agent and then say .start. Then the framework will tell us when a request starts. And so then we start a transaction. But now the interesting part actually for us is at the end of a transaction. Okay, so we do a bit of logging and a bit of argument handling, which is not that interesting. Capture breakdown here just records the name and the type of the transaction, like is it background processing, like a custom one, or is it just request for a standard request? We do a bit, this is like some edge case handling. Then finally, we call on the instrumentation module, specifically the add-ended transaction function. Yes, which calls transaction.encode. So we're out of the instrumentation module and back into transaction, okay, where we are going to look for the encode function. There you go. Okay, now the salient bit here is to JSON. Okay, so further serialization, basically. All right, so let's go and have a look at that. We record things like the trace ID and the parent transaction ID. So this is for this distributed multi-colorful tracing that you saw, requests being tracked for different services. The type of the transaction, request or backend job, and some other metadata about the transaction. Now, if the transaction is being sampled, which by default is all of them, and we want more information, and here we finally get properly into it, Now, for performance reasons, usually you'll be okay with just sampling every transaction, recording spans and details about everyone. But if the agent is impacting you in production, then you can say, well, only sample 10 or 20% of my transactions. So that's what that's the implementation of this, basically, and this principle. So here we have 3 different parsers: get user context, get the context, the rest of the context from each request, and then get it from each response. Now, I think it might be helpful at this point, because I've been trolling through code, for you to see the diagram of it. So, error is fairly straightforward: handler, capture error, and then we call the Node.js function. In green, we have third-party code. In blue, we have our agent. And here, transaction end jumps quickly to instrumentation, then back to encoding itself. And here we are, the 3 parsers that we're going to look at now: the user context, request, and response. Okay, so let's start with the user context. And this is essentially just us, well, not really guessing, because there are certain conventions that libraries will typically use in frameworks for recording an authenticated user. But we get this, we don't do anything like hyper low level for this. We get this supplied from the request object, which is supplied to us by Node and the web frameworks in use. Right, so from then on, we simply look at user ID, username, or email. We just try to look for the field. It's as simple as that. And then we return that, put that in the final result, and send it off to APM server. But what about the rest of the context? Okay, so let's look at the request first. So in the request, we capture method, URL, remote address, and we make a copy of the headers of the request that we are preparing. Okay, let's just remind you of that looks like in UI. So if we pick this transaction, here we have the request, headers being recorded right here, and you can see here, yeah, the method is get, the remote address is localhost and IP version 6 for some reason, and so on and so forth. That's how we record it. And this is how we get it. Just applied to us by the libraries, and we simply pick it out. Then we will capture there is an option to capture body of transactions. So it's quite useful if you return errors in your other services in the body as JSON. This is pretty interesting as a temporary fix for an issue, which in January will have its 2nd birthday. So it's the nature of temporary fixes, isn't it? It is simply to do with the data type. APM server required ports to be strings, and now it does actually accept integers. But yes, for backwards compatibility, is valid for keeping around. Although you definitely want to upgrade your agents and APM server at the same time, unless you absolutely cannot. Definitely do it at the same time. All right. So then, what do we get from each response? We'll get the status code of the response, of course, and we will get the headers. And we use a third-party library to parse out the headers, because this could be external services returning a result, and who knows what their servers will decide to return as a header. And that's pretty much it. So here, I'll just remind you in the UI. There is our status code, and those are our headers. Things like content type are, of course, super useful. And so that's it. That's how we obtain this tracing data. Now, how do we get stack traces? Because I promised you that. So we've looked so far at how errors come about and get grouped, and we've looked at these parsers and where we get request and response data from, and we do rely a lot on third-party libraries to get that. And all of it is mostly just building a JSON object and sending it, like picking a few bits of info from third parties and sending it on to APM server. Now, stack traces. So there, for that, when you start a transaction, it will add at least one span to itself, and that's where our journey begins. So we have some imports, and we have the constructor, we have some not so interesting options handling. But if we've configured, which by default we do, if we've configured the agent to capture stack traces, then we call record stack trace, same file. So let's go and have a look. So there's an error, then we rely on the Node.js function, again familiar from the uncaught exceptions handler. We rely on that to give us the information we need, or alternatively, the really interesting bit is this. We use a third-party library called Stackman to get the stack trace full frame. And then we put that together in a piece of JSON, then send it on upwards to the APM server. So let's have a look at that parser. And so here you can see us taking information out of that Stackman library and getting exact things like file name, the line number. This is interesting. So remember how we had whether pieces in library, whether a piece of the context is library code or our code. So we get this also from the Stackman library, and we'll see in a bit how it. Actually, let's have a look now at how it does that. It's quick and easy to see. So it does it by determining whether the code is Node.js native, which it does over here, by a bunch of, let's say, lower level detection techniques. And but the curious thing for me really was this. So how does it detect library, that it is in the library? It's okay, whether it's Node or not, you could see that. And that is how it does it. It just looks at whether the execution file name contains Node modules and the separator. So that's pretty cool, right? You get this feature, and like at least when I looked at this, I was like, whoa, this agent must do something quite interesting to get this info. It's so advanced. It looks low level into things. And it does, and like Thomas Watson is actually the author of this third-party library, the person who spoke earlier at this conference. But it's also something that's totally understandable. All right. Well, so you've pretty much seen how we get the stack trace. You've seen how we get whether it's a library piece or not. Now, if we have a quick look. Let's see if we're missing anything. I'll have a look at this Node.js thing. So whether it's a library is here, stack trace, as overall all of this. Yeah, the context. So how do we get the actual code? We get this from Stackman as well. And we get it right here, called source context, and then simply retrieve it. Like this. So I think, unfortunately, in terms of time, we should move on. Otherwise, it could dig forever in the internals. So now you've seen how we get errors, how we get the transaction info, and things like the headers and the body of request and response. and how we get our stack traces, file names, line numbers, and so on. Now, overall, this fits all. How does all this fit in the Elastic Stack and within monitoring more generally? If you haven't heard of the Elastic Stack, Elasticsearch, open source, analytics, and full text search engine, so you can throw text at it and numbers. And if you put dates on each record, then that's time series data, and that works really well. And it's also really, really good at returning the full text to you by a number of very powerful different queries. But today for monitoring, we've been using Kibana all throughout today for the user interface, and that's what that is. Beats are lightweight shippers that will just take things like just log files or other information, like packet beat takes network information, metric beat takes CPU, RAM, etc. for your host or Kubernetes cluster and sends it on to Elasticsearch. Logstash is a powerful log parsing engine. So altogether, you do logs and metrics with this. So, and that's how that's where the company became famous, like after the open source Elasticsearch project became popular. So, how does tracing fit within that? It's alongside those things. And I would say if you're starting a new project, start with the tracing because you also get some of the benefits of logging, like the grouped errors, and you also get some of the basic metrics, at least CPU and RAM. If you want to learn more about all this, first, try setting the agent up yourself. Second, watch the Trouble with Tracers talk, again by Thomas Watson, who's the author of this agent, the author of the Stackman library, and who also talked at this conference earlier. Watch this talk. He goes into some interesting detail about how tracing happens for individual libraries and how instrumentation happens. Then, of course, you can go and get the open source code. And if you use the diagrams from my talk to get an overview of how the whole thing is put together and is working, then that'll be a good start for you, a scaffold. And then you just dig into whatever catches your eye. If you have any questions, I'm here to answer them. You can find me on email and on Twitter. Thank you for your attention and for listening to me. Stay healthy and stay safe.
Hey, we are back. So thank you for your talk, Emanuil. I know I'm a bit biased, but I think it was amazing. Learning how things work behind the scenes is always worth it and also fun, I will add. And a question that I want to ask you is, does using an APM agent slow down our application in production?
So usually it doesn't slow down by very much. We generally say that it depends, depending a lot on your hardware and on your application. But from colleagues in consulting, I've heard single-digit impact in percentages, so like 2, 4, and it varies greatly between clients. So I assume the JavaScript agent is similar. But if you do find that weighs down production, we do have something to help with that. So if I quickly share my screen with you, I have this page called the performance tuning page. This is for the Node.js agent. And here there's 2 really heavy hitting things. There's tons of stuff you can change. One is sampling. So by default, we'll get detailed information and the spans, these blocks are showing for every transaction. But you can make it be like 10 or 20% of the transactions. So if you have that many, then presumably it will still be statistically pretty significant. But that's one huge way to reduce the load. Obviously, you're not processing like 80% of the stuff. And then not getting the stack traces for spans, like the third part where I showed that you get down to line number. If you're not really needing that for every span, but like you only want it for errors, then you can ditch that, and that's also supposed to help with both CPU and memory. So those are two big things you can do.
Okay. So another question we just got in the chat is there an easy way to implement APM in an application that you have already built? So you want to start observe more your application. What should you do?
Yeah, totally. Yeah. So I would start with putting APM in the backend first, actually, just because people usually find it a little bit easier to deal with and understand what's going on, especially the numbers, because they will have some idea of what their backend performance is like. But as it was seen in the talk, it's just a require, and then it's the minimum is to one line of config, the service name, and that is it. And it starts instrumenting, so you can absolutely add it to an app.
I can see where this question is coming from, because I know you can do a lot of stuff with not only the Elastic APM, but any APM really. You can monitor almost everything. I remember talking with both you and Thomas. A cool part of the APM is that it automatically monitors everything HTTP related, which is pretty cool. So a question I wanted to ask you is how do you do the distributed tracing between services that are not actually using HTTP as a communication protocol?
So for that, you can send, and I have to thank Thomas, the author of this package, for this knowledge here. For that, you can take the trace ID from the APM agent, because we give that to you, and you can then transmit that to those services using whatever protocol they're using. And then you can start a new transaction based on that trace ID. And it's a similar mechanism to if you wanted to do log correlation, which is also something we support. So in addition to the pre-built APM dashboards, if you wanted to connect to see the logs from all the services that the request has gone through, Python, Node.js, doesn't matter, like real user monitoring. If you want to see for the logs for all of them for that specific transaction, you can actually enhance your logs with that trace ID. And it's in a similar fashion, you can give the trace ID to those services using whatever protocol they're talking in.
Okay, cool. Thank you. So I have one last question for you. So you said we have the Node.js APM agent, but also the real user monitoring, which is something you use on the browser side. I mean, it's still JavaScript in both cases. What is mainly the difference on a high level between these two agents?
Well, it is indeed mostly JavaScript. And to be honest, the core structure remains roughly the same. Like they'll still have the same breakdowns, transactions, spans, and so forth. They're just basically different in primarily in how they're oriented, in what frameworks they support, and in how they approach things, I guess. Like if you see the structure of the two clients, they're just written quite differently as an overall design. At least looks that way to me. But it's the same thing, and that's kind of the point of my talk. Really, there's nothing that supremely magical about it. You have transactions that you can break down into spans, and you rely on third-party libraries. So in the case of real user monitoring, could be React and Angular and Vue. And in this case, it'd be Node.js, Express, etc. They'll tell you when a request starts and ends, and that's indeed what the real user monitoring agent does as well. It captures a bit more info, like it captures things like the browser, for example, and has like a nice maps of where your users are connecting from and breakdown a browser that they're using. Obviously, you don't get that in the backend ones. So.
Okay. Well, thank you a lot for the talk. I know there is an ongoing work in Node for improving the observability situation, which is definitely not the best at the moment. I mean, the Node core can and should do more for helping you in that. And there is an ongoing work on a module, a core module called the diagnostic channel. I'll share the pull request link in the chat in a moment, which I'm fairly sure our engineers will be extremely happy about. So thank you again, and catch you the next time, as I said before, hopefully in person.
Oh, thank you for organizing.
Bye.
Bye-bye.